Hi, welcome to this video about ZP technologies for the teaching at labs for biomedical engineers. So we're imagining, or not imagining, we're supporting the training of biomedical engineers really through biosensors. So what we'll do today is talk about glucose sensors, and I've also got some hardware in front of me, so you can see put my hand on it now. And we'll be talking about, I'll be doing some practicals with this shortly, but so wait on for that. But primarily, we'll talk today about glucose sensors, and we'll also talk about potassium sensors. And then I'll be using a SenseItAll platform. The teaching that you'll be doing by watching this video and then maybe translating this into your own lab practicals for undergraduate teaching, for example, you'll use the SenseItAll, but just know that this is also just as applicable to wearable biosensors as well. With that said, why should biomedical students even care about biosensors? And I also want to add the term wearable biosensors there. And really, from an academic teaching perspective, it's because biosensors for biomedical students really are kind of bring together all the disciplines. So we're talking about biology. So whether you're testing in blood or interstitial fluid, this is a biological system that we're measuring. There's definitely chemistry involved in this. We're talking about things like glucose, glucolactone, hydrogen peroxide. Chemistry is definitely part of the story here. We'll also be talking about biochemistry. We're talking about enzyme kinetics here. I'll mention Michaelis-Menten shortly. So this is definitely a biochemistry video as well. I'll also be talking about electrochemistry. The modalities that we'll be using this afternoon in this video will be amperometry and open circuit potentiometry. Amperometry for glucose sensing, open circuit potentiometry for potassium sensing. Material science, definitely when you're talking about biosensors, you'll be talking about things like polymers and printed electrodes, etc. So material science is definitely something that will pop up as well. Now I've cheated a little bit and put electromechanical together. Electromechanical is such a discipline in biosensors, especially wearable biosensors, when you're talking about having something affixed to somebody's body and you're continually measuring, probably through microneedles, into that interstitial fluid. And really, something that we haven't historically appreciated, but I think we do now, that really a biosensor is just a conduit for data. So we are getting into the realms of data science as well when it comes to biosensors as well. And in the next few years, you'll start to hear people say, all right, well, AI has got as far as it can get with large language models, and you'll hear them saying about real world models. So we will be, if you're teaching biosensing and you're teaching biosensors to biomedical engineers, and you're really starting to actually teach them to create conduits for AI, and that'll be AI based on real world models. With that said, let me start off with a glucose sensor. So I've got this series of QR codes, and in fact I've got a real world sheet in front of me here. And these QR codes work in conjunction with a app we have called SenseItAll. So SenseItAll will allow our app to know what to do essentially. So you'll see that in a minute, that I'm going to scan one of these QR codes. So what in fact I'll do is I'll be scanning the QR code for amperometry. Now with the glucose sensor that you can get as part of the ZP technology stack for teaching biomedical engineers, it'll have an enzyme associated with it, it'll have barrelase associated with it. So these sensors come pre-functionalized, where the glucose will react with the enzyme and you will get glucose converted into glucolactone, and there is a reaction with the enzyme with a cofactor for glucolactone. The cofactor for glucose oxidase. The cofactor for glucose oxidase is actually oxygen. So oxygen gets converted into hydrogen peroxide, and hydrogen peroxide will diffuse to an electrode where it is detected by the application of a potential. So now we're getting into the realms of electrochemistry. So electrochemical biosensors, one example of that is glucose sensors. Glucose sensors are really commercially and both commercially important and healthcare important, because in healthcare, glucose sensors are used in diabetics for testing the blood of diabetics, and also used in wearable biosensors as well. And especially in the wearable biosensor front, the reaction ultimately at the heart of these is often the conversion of glucose into something that's electrochemically active, like hydrogen peroxide. So if you get the ZP sensor from ZP, that's effectively what you're doing. Now it says here demo, so what I'm now going to do is I'm going to actually stop sharing that, and I'm actually going to go to my external camera here, and I have a biosensor in front of me. Now the first thing that it says is on my phone, on the SenseItAll, it says open circuit potentiometry. I'll bring in this sheet here, and I'm going to scan Amperometry. So it says at this point Amperometry on my phone, and it says device connected, which is all very cool. So what I'm going to do is I'm going to start off by putting 50 microliters of just no analyte onto the sensor. Analyte, can mean glucose or potassium depending on which sensor we're actually using. So I'm just going to put 50 microliters onto that sensor to start with, which is now on. I'll go to my settings. I'll go amp, because I'm doing amperometry. I'll go demo so we can find this shortly. And we're basically good to go. I'm just going to, yeah, that's good. I'm just going to go continue here. So we'll do something like 90 seconds, that's fine. I'll do one save point per second. I'll do a potential of 650 millivolts. I'll do 10 microamps. I'm going to actually start that now. So we've got a couple of things going on. So I've got the 0 millimolar solution on the sensor. I'm going to just perturb it quickly with a shot of analyte. So let that sort of find its 0 point. I'm just going to check. Yeah. I'm just going to do a quick refresh on another screen. So that's kind of settling to a baseline. It starts off, the current starts off high and then falls down. This is a charging current, and then it finds its baseline. Now I'm going to give that a little challenge or a little addition of analyte here. So boo, 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 boo. And then the signal would sort of jump up there, and it won't come back to the original thing, because now we had a baseline at 0, it spiked up, and now it'll come to a new baseline that's higher, because that's the sort of analyte concentration. We've got about 40 seconds left of that. So very shortly, I'll let that run in the background, because I just want to share my screen here with you. Yep, that's doing that, and I'll turn these two on. Because what it's doing is it's running, it's got about 25 seconds left. When it's finished, this is a very modern system. It'll send the data straight to the cloud. We have a cloud system called Julie. This is the SenseItAll platform. SenseItAll meter, electronics, contains the electronics. We've got the sensor on here. The meter knows what to do because it's in Bluetooth connection with my phone. The phone sent the command to the meter, and I knew what to do because I use the QR codes. At this point now, the measurement is finished, and my phone says upload complete, and that means that the data has actually gone to the cloud. So I'm just going to do a quick refresh here, and it will show me a new data set here, which is called Amperometry. Oh, I just put amp in for it for short, and that's essentially the completion of, let's say my demo, but I will have some more slides, so hang on, and I'll also be doing an open circuit potentiometry measurement in a minute as well. You can see that for undergraduate teaching, this is quite straightforward. So I can see here my original baseline, then I added in the analyte, and now you can see essentially the new signal here. Now I can start doing all sorts of analysis on this, and if you so wish and you want to use this, then reach out to us for maybe a more in-depth demonstration. But let me just switch now to, so that says demo. So what's happened here is you can do a series of experiments like the one I just did, which is amperometry, where you can actually add different amounts of glucose. And in doing so, we start from 0, we can go to 5, we can go to 10, we can go to 15, we can go to 20, and you can kind of plot them all out like that. And that's sort of showing you, that you have a current, let's call it signal versus concentration. But I'm also going to give you a little slightly, if you're teaching and you want some sort of theory to kind of go alongside, this is a glucose sensor. You can also teach them that the kind of Michaelis-Menten kinetics and equation are at the center of this, that you've got this glucose molecule that's sort of binding with the active site. So we've got E plus S, when S means substrate, and in this particular case, glucose. So there's a kind of on kinetic, which I call K+1, and there's also an off kinetic where the glucose kind of decouples. And now, if that's all the enzyme does, then it's not a very interesting enzyme. But really, what enzymes are doing is they're forming this complex based on the ratio between K+1 and K-1. But then the complex also has a forward path, which is, I call it K-cat here, where actually we go on to form the product. And now in the case of glucose, glucose oxidase. This is glucolactone. You'll see in some literature it says gluconic acid. That's because glucolactone has a following hydrolysis reaction, but the first product is actually glucolactone. So we got enzyme plus product. Now the conversion of substrate to product happens at a certain rate, so we call that V here. And you can characterize a glucose sensor or any kind of Michaelis-Menten based sensor by looking at rate, which in the case of a glucose sensor is also current. And you can show that current versus substrate concentration can be kind of linear for at least lower concentrations. But there's a point with enzyme sensors when enzymes don't have a finite amount of activity, and you actually can start having more substrate than the enzyme can necessarily keep up with. And so a glucose sensor can actually start to showing a sort of tailing off of rate or current with glucose concentration. I mean, at ZP we can make sensors work up to 20 millimolar, maybe 30 millimolar, but typically if you start trying to use 50 millimolar, for example, you'll definitely hit this kind of flattening off region. Now, anyone who's familiar with Michaelis-Menten will know that when it starts to plateau off, we often refer to that as the Vmax. But that curve can be characterized by this Michaelis-Menten equation. At very high concentrations of substrate, then the rate is actually proportional to Vmax. So you can estimate Vmax by just imagining the plateau region, and that will tell you essentially what the Vmax is. Half of the Vmax kind of indicates the linear region of that sensor, and we can call that kind of Km. So you can do a testing of glucose sensors from ZP using the SenseItAll platform, using different concentrations, and you can show the signal versus concentration. And if it plateaus off, you can justify it by referring back to the Michaelis-Menten, which is governing the underlying enzyme kinetics. Now I'm going to change direction slightly here and talk about ion selective electrodes. So you can teach biomedical engineers a lot about biosensors by giving them a practical on glucose sensors, and you can also give them a good introduction by teaching them potassium sensors. And potassium sensors are a form of ion selective electrodes. So in fact, I'll grab one. The electrode looks let's say looks very similar to the glucose sensor, but this time it's been functionalized to be specific in this particular case to potassium. And I will carry on now saying, okay, we got two electrodes that we're using on the potassium sensor. We've got the working electrode, which has been functionalized to be specific in the case of potassium to potassium, and we've got the reference electrode against which we're going to measure the potential of that working electrode. The instrument, the SenseItAll, is smart enough to be able to go between the two, no sweat, and I'll show you how I'm going to do that now. So let me jump in and do a little bit more. So we're talking about open circuit potentiometry. So most ion selective electrodes, including pH, are using open circuit potentiometry. So it's a nice way of introducing to people in doing biomedical engineering that open circuit potentiometry is a way of getting biological data, especially when you're talking about ions. Now, here I'm sort of showing this mixture of ions, and what we try to do with our ionophore is have a surface that's specific to a particular ion. So in the case of potassium, we try to make the surface specific to potassium. Now, we have a signal when using potassium sensors. If it's ideal, we have a signal where actually we're proportional to the concentration of potassium times 59 millivolts. That's saying it's pure Nernstian behavior. I've got a little bit of a sketch here of what you can expect. So you can expect the idea that you have some potassium ions, they're on the sensor, and in changing that concentration, you'll find the potential changes and the signal will change accordingly. And you can plot that, and you can sort of say the potential versus the log of the concentration of potassium. Then you can add a bit more potassium and the signal will change again, and you can show that potential versus the log to the base 10 of potassium, and we can add a bit more potassium and we can show the signal changing accordingly. So this is basically showing us that potassium is a interesting analyte. People use it in sweat analysis, sometimes for hydration, sometimes they use it in dialysis to kind of show how well a dialysis patient is monitored, and the signal is proportional to potassium concentration, and you can do this raw signal and gather the data accordingly. Now, if this was a perfect sensor, which But selective electrodes, they very rarely actually come to 59 millivolts. So I would argue with a pH sensor you can actually get that. But that slope is approximately 59 millivolts. And if you extrapolate down to the y-axis, then you can also find the standard potential as well. So now what I've got here, written here is a demo. So what I'm going to now do is I'm just going to do I'm going to go to a camera here. And I'm just going to demo in real time. So let me grab my phone. It's the same journey as before. What I mean by that is if I show you my phone now and I go done, it says amperometry, but I've been talking about potassium sensors and open circuit potentiometry for the last few minutes. So I'm just going to scan a QR code here, which then puts me into open circuit potentiometry mode. So now my phone wants to do an OCP measurement. So I'll take a potassium sensor. I'll put that like that. I'll grab just buffer and I'll put just buffer on the sensor. So let me do that. Now you can see how easy it is actually to set up this experiment. Some equipment in this kind of domain, in this kind of application space, can be all cables. And first of all, cables kind of mislead students that they think that, you know, this is modern electrochemical biosensing, and it's not. This is modern bioelectrochemical sensing. But I'll just put the solution like that, which I will do. Now I'll go to the software again and go, this is not AMP, this time it's OCP, come back. I'll go continue. I'll set the experiment time, 60 seconds, we'll do 1 data point per second. I'll hit start and it will start gathering a signal now. So just bear with me, this won't be that super long. So what it's doing at the moment is it's gathering just a signal without the analyte present, but I'll add some analyte in a minute. The signal will change accordingly, and I'll show you that the data goes straight to the cloud. So let me give it another 10 seconds, but let me do a quick summary. So glucose sensing, amperometry, very important both from a healthcare perspective, but also from a commercial perspective, because glucose is obviously very much tied to diabetes and diabetes control. I'll add this analyte now. Then I've actually changed the instrument over now from amperometry to open circuit potentiometry, and I've just added the analyte, and the signal will change accordingly. And you'll definitely see that this signal is basically sent to the cloud, and I can do analysis on it. But you can have the students do a series of increasing additions of, for example, potassium, and send the data and analyze and see what their gradient is, see what their intercept is, and then they start to understand that there's a nuanced equation behind this. So you can kind of tie theory with practical, which is something that we really like to do at Zimmer and Peacock. I'm just going to share my screen with you for a second, which is what I'm doing here. I'll go to reports. I'll do a quick refresh here. We'll see OCP, so just bear with me. I'm only going to be another minute or two. And there's the OCP. I can do a much deeper analysis using the Judy software. It's really good for that. But I'm just doing a sort of an introduction on this at the moment. It's probably worth saying that when we ship these kits, we ship the SenseItAll, we ship the sensors, we ship the test solution, we also ship wash solutions, so you can reuse the sensors as well, and the signal's quite apparent there. So let me just go to my last few slides and just say, in summary, biomedical engineering, a really important science actually, both from a healthcare perspective but also from a commercial perspective. Teaching biomedical students about biosensing, starting with glucose sensing and potassium sensing, is good. They're both robust sensors, they both have real world application, and you can sort of teach them amperometry, and you can teach them open circuit potentiometry as well. You saw I used the SenseItAll to do all of that work, and if you do have any questions regarding the teaching of biomedical engineers using biosensors, then ZP has a good platform for this, and don't hesitate to reach out to us. Okay, thanks very much.